Hello, everybody. Welcome. I'm Eric Iverson, Managing Director of the Wisconsin Alumni Research Foundation, or WARF, and welcome to WARF's Essential Topics. WARF's Essential Topics is a series that looks at important issues that affect how we work with campus and the business community, whether through the eyes of protecting intellectual property, moving inventions forward, or adding value to the research enterprise. Today we share a special opportunity. We get to enjoy a very rare behind-the-scenes look at a discovery truly in cosmic proportions, and we get to hear it from one of the visionaries that made that possible. Over 2 decades, WARF has supported the IceCube project through early research grants, a professorship, and matching funds for the National Science Foundation grants. In all, about $1 million that WARF has provided in support. Our foundation made the decision to support the project at a very early stage when the outcome was still very much unknown. This early support came at a critical moment. It helped Professor Halzen's team establish the first proof of concept neutrino detector in Antarctica, a project called Amanda. It also helped convince a skeptical scientific community that the project was practical as well as imaginative. WARF supports scientific adventures such as IceCube because the legacy of this campus compels us to be bold, to invest in risk, and to extend the Wisconsin idea to the edges of the world. This is our mission and WARF's privilege. Consistent with that spirit of partnership, IceCube has become a proving ground of international collaboration. What began as a theory and proof of concept has bloomed into a scientific enterprise encompassing more than 300 researchers and dozens of institutions around the globe. Today, we learn more about the latest chapter in this great experiment. Before I introduce today's presenter, Professor Halzen, I'd like to mention that we have a Q&A at the end of his presentation. The doctor will speak for about an hour or so, and then we'll have some time for your questions. Please wait for us to bring you a microphone as we are recording this presentation. With that, it is my sincere honor to introduce Francis Halzen. Dr. Halzen is the principal investigator of IceCube, and he is the Hilldale and Gregory Bright Distinguished Professor at the University of Wisconsin here in Madison and director of the UW-Madison's Institute for Elementary Particle Physics. He earned his master's degree and PhD in Louvain, Belgium. He is a principal investigator for the IceCube project, the world's largest neutrino detector. Among his many recent honors, he was elected to the Royal National Academy of Belgium in 2016. In 2015, he was awarded the Balzan Prize for Astroparticle Physics, the European Physical Society Prize for Particle Astrophysics and Cosmology in 2015, the Smithsonian American Ingenuity Award for Physical Sciences in 2014. Where do you sleep? When do you sleep? The Physics World's Breakthrough of the Year Award for making the first observation of cosmic neutrinos, the American Physical Society Highlights of the Year, and the University of Wisconsin's Hilldale Award in 2013. Dr. Halzen is the author of more than 700 research publications and a number of honorary degrees. I am absolutely blown away, and it's truly my honor to introduce you. Please welcome me in joining Dr. Francis Halzen.
So now I don't have to say the nice words about WARF, but what was really true is that WARF gave us $1 million when nobody would give us a cent. We were, I'm not going to talk about this, but there were many, many moments when we thought this project was dead, and that was one of them. And so thanks to WARF's funding, we got it out of solve our problems. Okay, ice fishing for neutrinos. So this is the South Pole. It's a picture taken by one of the winter rovers, and So that's as pretty as it gets. South Pole is a desert, so if you come for pictures of penguins or anything else, that's it. And what's special about the South Pole is that you stand on about 2 miles of ice that's ultra transparent. And you know, we are going to build a particle detector out of this ice, and so what's important is how clear and how transparent the ice is. And I cannot show you a picture of the detector, but if you go to the coast, you can imagine that's what the ice looks like. And you can imagine a big block of ice out of this that's, perfectly clear. In fact, we discovered, and I really mean discovered, this was pure luck. We had no clue when we started this, that blue light travels typically like hundreds of meters through this ice without being absorbed. And in fact, it's impossible to purify water that's this clear. And it's impossible to build a solid in the lab. So, if particle physicists had a dream of building a detector, they would use this ice. So where is the South Pole? The South Pole is this dot here. And this is a picture from a C-130 plane that brings everything into the South Pole along this runway. And our other piece of luck is that the National Science Foundation had a research station there that allowed you to build this experiment. In fact, that's Ice Cube on the other side of the runway. And maybe one pretty picture, just to remind you, that's the South Pole Station during the winter. And you can put people there year-round, which is important for this project. So now comes the long road to what we finally found, that I will tell you in the last few slides. I don't assume that everybody in this audience knows what a neutrino is, what cosmic rays are, what neutrino astronomy is, and then I will tell you what Ice Cube is, and tell you what we found. A neutrino, actually, even if you don't know, you should know about it, because you learned in school that matter is made out of these 3 particles. Protons and neutrons that make nuclei, and then you put electrons around and make atoms, and we are all made of atoms. Well, that's not the whole story. And what's wrong with this picture was discovered in the 1930s in Cambridge, where people saw that a neutron occasionally decayed in a proton and an electron. And they noticed that this was actually possible. If you look at this picture, the electron and the proton go in the same way. That violates energy and momentum conservation. Billiard-ball physics makes this impossible. If the electron and the proton go in one direction, there has to be something going in the other direction to balance the energy, and that's the neutrino. And Ellis and Mott in 1933 discovered the neutrino this way, except nobody realized they discovered the neutrino. They couldn't believe they had discovered another particle when only 3 particles were known. Now we routinely use this to discover particles, called the missing mass, missing energy technique. But this was the smart man Pauli who proposed this solution, and he said this particle will never be detected, and he was close to true. And so this is the complete table, and it's very important actually. The neutrino is actually the most common of these particles. If you count in the universe how many of each there are, the neutrino wins. And so what does the neutrino do? As you saw from my previous slides, the neutrino makes it possible to change protons in neutrons. That's called nuclear physics. And so there are neutrinos wherever nuclear physics happens. the Big Bang, when stars explode in the sun is a nuclear reactor, the Earth emits neutrinos, you emit neutrinos from soul decay in your body, accelerators, Fermilab 2 hours south of here, make neutrinos, and this is an important picture. Here you see that's a nuclear reactor, and you don't see the neutrinos, but they cover these nuclear reactors with water. And notice where there is a nuclear reactor, there are particles coming out that are shielded by this water, and this water turns blue. That blue light is important in this talk. Then you make neutrinos when cosmic rays hit the atmosphere, and they make pions that decay neutrinos, and I will come back to this story in detail. Neutrino astronomy. Why would you do astronomy with a particle that barely interacts? Well, the basic problem is twofold. You know, astronomers have been very successful at doing astronomy with different particles. In fact, they always do astronomy with the same particle. It's called a photon, the particle of light. And of course, astronomy started with Galileo pointing the optical telescope that had been discovered in Flanders, but never turned at the sky, towards the moon and Jupiter. Radio astronomy was discovered by Jansky in Aurora, Illinois, and etc., etc. The reason you want to do neutrino astronomy is you want to join this table. What this table shows you is why people built the telescopes and then what they did with it. And there's never any connection. They always saw something different than what they were looking for or thought they were looking for. And what they saw was always much more interesting than what they could imagine. And you want to show this table that you can typically find in an elementary astronomy textbook. That's the real reason. Notice, you cannot write this reason in a proposal because then it looks like you're gambling with the government's money, but that's a different question. I can be honest here. This is the sky in light. If you were not living in Madison, you would see the galactic plane. And I'm showing you this to remind you, I will always show a map of the universe with a picture like this, and things that are happening in our own galaxy line up along this major axis of the ellipse. So now I'm going to follow my table, and I'm going to go to bluer light, very blue light actually, that you cannot see with your eyes, 10 to the minus 4 electron volt photons, and this is the sky, this is the microwave background. No, I mean I'm going to the red part of the spectrum, sorry. If I now go the other way from visible light to the blue, the sky looks like this. You notice how you always find something different, looks totally different. And in fact, here you see there are a lot of sources in our own galaxy. And so you can do that. You can go to redder and redder light and bluer light. And unfortunately, if you go to bluer and bluer light, you go to higher energy radiation, the sky turns black. It doesn't work. And that's the sky we are going to cover with neutrinos. It has never been seen before. Why is that? If you take a gamma ray of this tiny wavelength or very high energy and you produce it somewhere far away, it never gets here. Because I showed you the microwave background. The microwave background shows that throughout the universe, there are 410 microwave photons in every cubic centimeter. In this room, in our galaxy, in the whole universe, back to the beginning of time. So the universe is not an empty place. In fact, there's all kinds of light, but it's dominated actually by these microwave photons. And when a gamma ray makes its way to our telescope on Earth, it never gets here. It hits one of these microwave photons, 410 per cubic centimeter, makes an E plus E minus pair, and astronomy is finished. You cannot do astronomy with charged particles. In fact, the highest energy radiation in our universe doesn't come in the form of radiation, it comes in the form of particles. And we don't know where they come from because they're charged. They are mostly protons. And so to summarize this picture, I have summarized this on the next slide. So this is the sky from microwaves over optical to X-rays to gamma rays, and here is where the sky turns dark. How far does this go? Well, we know we see cosmic rays. We don't know where they come from because they are charged. I mean, if they're charged, they are bent by the magnetic field of the Earth, by the magnetic field in the galaxy, by the magnetic fields outside our galaxy. So a proton can be produced there and arrive from there because it swirls in these magnetic fields. But we know their energy, and we know that the universe extends at least to this energy, 10 to the 20th electron volts. I come back to that. And you see, this is a universe that we know exists, but we have never seen it. That's where neutrinos come in. So why is this an interesting place to look? Maybe it's just boring. Well, these cosmic rays, first of all, as you saw from my previous plot, this is the highest energy radiation that reaches us from the universe. We know it exists since 1912, when Victor Hess went up in a balloon and saw that the radiation actually increased when he went higher and higher. He went to 17,000 feet without oxygen in his Sunday suit. And he saw the radiation he detected go up, so something was coming from outer space. We know some of this stuff comes from our own galaxy and some comes from the whole universe. And I remember in '91 when an experiment in Utah detected one of these protons with an energy of 300 million TeV. Now, it doesn't matter what a TeV is, it's 10 to the 12 electron volts, but it's the energy of the collider at Fermilab that doesn't exist anymore. And 13 TeV is the energy of the Large Hadron Collider. So this particle has 10 million times the energy as the one accelerated in Geneva. And so I like to show this slide. If we would take the magnets of Geneva, in order to accelerate that particle, you would have to fill the orbit of the planet Mercury. Now, if you're a particle physicist, you know, you can spend your life trying to how does nature do this? Where does nature do this? And we have no clue. We had no clue. Now we have a clue, as you will hear. So I explained this already. And of course, you realize neutrinos, they have no charge. So you can do astronomy with them. The only problem is they are very difficult to capture because they don't interact, as Pauli told you. So this is the propaganda. They are neutral. They are essentially massless. They have a small mass, which we don't care about. So they're exactly like light beams. And they track nuclear processes. Remember, they only happen where nuclear physics happens. So when you make a map in neutrinos, you not only will see cosmic ray accelerators, you will only see cosmic ray accelerators. So it's just the right way to do it. And so the neutrino was actually rediscovered in 1956 by putting an experiment near a nuclear reactor. And the man who did the experiment told me that as soon as they published their results, everybody had the idea to do this. So the idea goes back to the 1950s. How to build this detector was discovered in 1960. I'll show you a picture of the man later. And that you needed a kilometer cube detector because you don't detect neutrinos with a mirror was known since 1969. So this was a problem of developing the technology to do this. All the ideas were there before 1970. And so how do you build, cannot build detect neutrinos with a mirror, so you need a kilometer cube particle detector. And Markov had this idea in 1960, and the idea is shown on this slide. So you see, what he proposed is to go deep in an ocean or a lake and fill a kilometer cube of water. You pick your kilometer cube of water and fill it with light detectors. And then the way you detect neutrinos is you detect particles coming through the Earth. Only neutrinos come through the Earth. And what they do is they just fly through your detector, like Pauli announced in the slide I showed. But in our energy wavelength range, about 1 in a million neutrinos don't see atoms. They only see nuclei, and they only interact with them very weakly. But occasionally, they will hit a nucleus and then make a nuclear reaction. So they make like a small nuclear reaction made by one neutrino. And the neutrino will then disappear, and it makes other particles. Some of them are charged. Now, instead of a neutrino, you have charged particles, and charged particles in a clear medium like water make blue light. Remember the reactor covered with water that turned blue? This water will turn blue. And if this is a muon neutrino, there are 3 types of neutrinos, we don't care today. But 1 in 3 times this neutrino will make a muon. And I will not introduce any more particles, so this is all we have to know. The muon is like a heavy electron. We don't know why it exists, but we are very happy it exists. Because this muon, unlike the other ones, will travel kilometers through the ice. And when it reaches your detector, it will make blue light. And the blue light, the muon, goes at the speed of light. Whereas the light in water goes at 3/4 of the speed of light. So the muon outruns the light it makes, and so it makes a shock wave. Just like a speedboat outruns the speed of the waves on the water and makes a bow wave. Exactly the same thing. What are light sensors? Light sensors are photomultipliers. They are like light bulbs, but they detect light instead of making it. And you can see one here. The bottom of this, what we call digital optical module, is a 10-inch light bulb. It costs about $1,200. And you buy many of them and you have a detector. So all the physics that go into this you can understand. There's nothing magical. The blue light is this, same blue light, and the fact that you can reconstruct the direction of the particles is the same reason as this. Even if you don't see the duck, you see the waves, you know which way it's going. So we have not only a neutrino detector, we know where the muon comes from, and the muon and the neutrino are aligned, so you know where the neutrino comes from, so you have a telescope. I think I said all that. People build a detector in Japan, just like this. You see water and light bulbs. These light bulbs are bigger than ours. They don't have to pay for them, they are made in Japan. And so what they are going to do is, this is a tank that's about the size of this room, but much higher, like 5-6 times higher, filled with 11,000 of these light sensors. So here you can see another picture of this. And why can't they do astronomy? It's very simple. This is 10,000 times too small. You have to build something 10,000 times this size. This was tried by a bunch of brave people off the coast of Hawaii in '87, and they discovered many of the techniques that we used and borrowed from them, but their experiment failed. And so then the idea came up here in Madison. We started working on the idea, and that's the only place where I think if we were ever clever, we were mostly lucky. But here we were clever. We actually realized it's easier to go to the South Pole, put these things a mile deep in the ice than put them in ocean water. And that turned out to be true. So then, of course, as I already said, we were lucky because this ice we found is snow that fell on Antarctica 50,000 years ago. It's compacted by the snow that fell afterwards, so it's crystal clear because it's totally pure. So I was a theorist and I didn't even have a lab, so what I did is I transformed our ping pong room in a lab, and this was the group that built the first optical sensors that were deployed. They all worked. This was the Amanda experiment that was referred to in the introduction. It was it took us about 7-8 years before we finally saw a neutrino. And let me go back to that picture, sorry. So this is the South Pole 2000, in the year 2000, and you see this was before there was really a station. So about a kilometer from the South Pole, we built this detector, this small detector. It's about the size of the Japanese detector. Again, too small. No, it's actually much bigger, but still too small. And it had about 700 of these things in it. And so we actually managed to find neutrinos, but these are totally boring neutrinos. These are the neutrinos I mentioned that are made by cosmic rays hitting the atmosphere. And but it showed that the ice could be used to detect neutrinos, and then we were in business. So you cannot quite, you realize you can see the direction, even though you don't see on the online display this cone, you saw the direction clearly of the track. So we published a paper and say, hey, we have a method to detect neutrinos, so now we are going to build 100 times bigger. And we did. So the way you do that, you publish in Nature and then go back to Washington. And that didn't go very well because people couldn't believe that, putting a mile deep at the South Pole photomultipliers in the ice was the real easiest way to do this. But nobody came up with anything better, and we were declared one of the 7 wonders of astronomy with Hubble, but in the category of the weirdest detector. I never knew what that meant, but it helped. So we did exactly what I advertised. You take a kilometer cube of ice a mile deep. The Amanda experiment showed that the ice was clear, there were no bubbles, you were in business. So you fill it with more than 5,000 of these objects. And how do you do that? So now I'm going to show you a 2-minute movie to get rid of the critical question. How does this work? And why is it actually rather easy? The top 90 meters is really easy because it's snow and you just melt it. Remember, you have to make a hole this big, 2.5 kilometers deep. So then you have this hot water drill, which is just a nozzle that melts the ice. The water comes out under pressure. And so after 2 days, it has fallen 2.5 kilometers, and you have water. So you need a 4.8 megawatt heating plant, which means 45 car wash heaters, that put out 200 gallons per minute of boiling water. So this whole structure is like a circus train, but it's not on wheels, it's on sleds. And this is this magical 2.5 kilometer hose. It's that big. And it can hang over 2.5 kilometers in water without collapsing. It's a marvel of technology. Here are the generators that drive the 45 car wash heaters, and so they will deliver the heat. So here you see the drill coming out. So ice is an insulator, so at this point you have a 2.5 kilometer hole that's water instead of ice. There's never a hole, right? And then the circus moved on to a different place to make more holes. But now you have, so as it's an insulator, this water is liquid for quite some time. And here you have the 80 of these ready to go into and sink into the water. And you see here comes the cable that comes down. Every 17 meters you attach one of these, plug them in, and then you have instrumented a kilometer of string, and then you let it drop to the bottom. That's it. That's simple. You do this 86 times, and you have a kilometer cube detector. Not always that simple, and this is not me. So if you could go in the detector, you would see a string every 17 meters, 60 of these, a kilometer long, and 125 meters away you would see another string, like from here to the physics department, and then another one, and that fills the kilometer. So this marvelous group of people that year, in 2 months, because that's the only time you can do this at a pole, December, January, when it's summer, had deployed 20 of these, instrumented 20 of these holes. And you see these are the cables that power the modules. You have to power it up, and then also you have to bring the data back digitally over this cable. You see there is a data board here. And what it does, it turns the light signals in digital signals that go through these cables to the top into this 2-story building, and in this 2-story building are the computers. So that collect this data and puts it together in these Cherenkov cones or whatever you ask for, they look for. So this is a muon. You see it enters the detector, that's the light it makes. This is an animation, and you see here the track, the muon track. This one came from above, so it's not a neutrino. So you can look at it again if you want. This actually, for the expert, is 1 photoelectron. And you see there's no noise in this detector. Incredible. So now I'll show you what a detector sees. Remember this, actually IceCube, while I'm talking here, detects a neutrino about every 5-6 minutes. And so what it detects is this. It's cosmic rays that hit the atmosphere. They interact with the nitrogen and oxygen, and then make pions, and these pions decay in neutrinos. These neutrinos then typically go through the Earth, but some of them will interact in the detector. And in fact, in this case, too many, as you will see. Because and also, with these neutrinos come muons. These muons, of course, have nothing to do with neutrinos coming through the Earth. They are just background falling from the southern hemisphere on our heads. So if you have a detector at a pole, you see this large rate of muons for which you are only protected by 1.5 kilometers of ice, and then you detect atmospheric neutrinos, neutrinos made in the atmosphere from everywhere on Earth. And so the way it works is you just take the data, you see all these data coming in. Each time you see a module colored, it means it detected light and send a signal to the detector, and the detector just fits muon tracks all the time to the light they collect. And so that movie you are looking at is 10 milliseconds long. So the balance is that we detect about 100 billion muons, atmospheric muons. We detect 100,000 neutrinos every year, actually many more now. But what we are looking for is cosmic neutrinos, and those we expected 10 to 100. We actually found 120 per year, so we did very well. And so what's a neutrino? Neutrino is exactly the same thing. It's a stream of light coming through your detector, but you see the color, red to blue. This one, you follow the rainbow, came through the Earth. So it's a neutrino, most likely an atmospheric neutrino. So how are we going to find in this 10 billion and then 100,000 neutrinos, how are we going to find this 10 or 100? And we didn't know very well ourselves, but again, we were lucky. And so I always tell people, as you heard, this collaboration by now 300 people. So once a week at 10:30 Thursday morning, you get into a room with your colleagues in Madison and everywhere on the world and connect by Zoom. And so everybody starts telling what they're doing. And you know, this is really boring, so everybody's doing their email and trying not to fall asleep. And I can remember when someone from Japan suddenly showed this picture. And I knew perfectly what they were doing, and they were not looking for this. They were looking for something completely different in the first 2 years of data. But when I saw this, I knew immediately this couldn't be an atmospheric neutrino or a muon. Notice there is no muon track. You don't see a track. And that's not a problem. It's an electron neutrino. And we could tell, you can immediately tell from the size of this explosion of light how much energy this neutrino has. And you know it's 10 times more than any neutrino can carry that comes from the atmosphere. So this was the real thing. In fact, we found 2 of these events and published them because our collaboration is so conservative, it cannot admit to itself that you can discover something with 2 events. So this is the event superimposed on the data center, which has 222 West Washington Avenue. And so you see the information in this event is incredible. Wait, it said in the previous one, there are more than 300 optical sensors and more than 100,000 photons. And we know where these 100,000 photons are to about this precision. And so we can reconstruct this energy with less than 10%, like a real particle detector, less than 10% error. So we know this is not atmospheric neutrino. And by the way, this, I don't have to explain what's in the picture here. So what we did is, the power was that this measured the energy of the neutrinos. We could show they were not atmospheric. And so we took the same 2 years of data and designed a method where we only looked at neutrinos starting in the detector. Forget what I explained to you earlier. And so we ground to the same 2 years of data and found 28 more events. So there they are, that's half of them, that's the other half. And then we published, we had discovered cosmic neutrinos. A few weeks later, we were declared the breakthrough of the year, and I can tell you most of us couldn't sleep at night because, what if this was not real? How do you ever run this back after this? This was, by the way, the year after the Higgs particle, which really deserved this. So the question, what about this? Well, while we were all doing what I explained to you, there, of course, you know how this works. There is still a graduate student somewhere sitting in an office, in this case in 222 West Washington, who was doing this. And he discovered cosmic neutrinos all by himself half a year later. And let me just show you one event of a beautiful neutrino. It comes 11 degrees below the horizon through the Earth, and it has the events I showed you at an energy of 1,000 TeV. This was as an energy of between 5 and 10,000 TeV. This event by itself is a discovery of cosmic neutrinos. So I should tell you how excited this is for the National Science Foundation, who gambled on us. Not only WARF gambled on us. In fact, WARF matched the 1 million you gave us. NSF matched the 1 million you gave us. But around the time that we were struggling to find cosmic neutrinos, the New Scientist, which is a respectable magazine, or it was, actually had you could bet on a web page. I'm not making this up, this is real. At the time, you could bet on a web page, and you could see the probability that we detected cosmic neutrinos. They would give 6 to 1 against us. They would give 500 to 1 against LIGO, detected gravitational waves. And you see, imagine, these were the big bets that NSF made almost 20 years ago. They decided they were going to gamble their money because that's the only way they could compete with DOE and NASA. Last year, within a month, both of the experiments started doing astronomy. So they had to wait 20 years. And of course, the web page was taken down because we all started to bet on LIGO. I'm a theorist, I know gravitational waves exist. And so, what did we see? Well, I cannot show you what we see because we have by now so many neutrinos that if I plot where they come from in the sky, it would just be black. So this is less than 1 year of data, actually. There are 120 cosmic neutrinos in this map. Can you see them? But I can, with the computer. And what's the surprise here? The surprise is that, look, you're first supposed to see sources in your own galaxy nearby. They, I told you, line up along the galactic plane. There's absolutely nothing. These neutrinos come from everywhere. So remember the galactic plane? Nothing. So they are a totally uniform distribution. Now I will help you. I will only take the ones that are cosmic and leave the other ones out. So what it means, I take the ones with very high energy, more than 300 TeV. And so you see the map and still nothing. There was a faint structure in this map, which has something to do with neutrino cross-sections. I won't go into that here. But you see, they are totally uniform distribution. You can, apply fancy mathematics to try to look for correlations to anything. In fact, this was the sad thing. We found this in 2013, and 5 years later we had analyzed this map in any way you can think of, or if you can think of a new one, come and tell me, and couldn't find no clue where they came from. So they came from sources distributed over the universe and came from everywhere. The first event we measured the direction of was this one. So it came right from the center of the galaxy. And so you cannot make conclusions with small statistics. So that was our conclusion. We do not see our own galaxy. This was a very important result. The number of neutrinos we saw, actually 120 a year of one species, 360 of all, was higher than anyone had predicted. And what it actually means is that neutrinos are not something rare or exotic. There are as many of them around as there are gamma rays that astronomers see. So they play a critical role in understanding the universe. So we basically start over now. And so we could not answer this question, which we had to answer. So this whole experiment, of course, was a desperation to find neutrino sources and cosmic ray sources. Now we tried something even more desperate. So what we did is, I'm not going to go through this, but what this slide tells you, the computers at the South Pole discover a neutrino. They realize it's a high energy one, not likely to be atmospheric, produced in the atmosphere. So what they do is, without any human intervention, they send the coordinates where it comes from as an astronomical telegram to all the telescopes in the world. And that's all. This happens in less than a minute. And then what happens is, you see it goes to the data acquisition system, blah, blah, blah. It's sent to a satellite, and the satellite throws it out to the world. And the satellite also sends it to Madison. All I do is I get an email message, that's all. There's nothing I can do. And then, of course, the data is looked at and make sure it's not some artifact or... So we had, and then, of course, we didn't know what happened. Maybe we knew some telescopes looked at it, some didn't. But then we tried this for 10 times, and then we sent this telegram, and this telegram corresponded to this neutrino. It's a beautiful neutrino like the one I advertised, and it came from the direction of Orion, and so we send its coordinates out, and soon after we heard that in that direction, the Fermi satellite, which detects the highest energy photons we see with our telescopes, the closest in energy to our neutrinos, found a galaxy. But not just any galaxy. It was a galaxy, I will tell you later exactly what this object is. It had increased its output in light by a factor 7 in the last 100 days or so. It's what's called a flaring galaxy. So that made it interesting. That made it a relatively rare object. In fact, the coincidence was 0.06 degrees. Really, by this type of astronomy, we really hit it. Then we found out there are telescopes that actually detect gamma rays from Earth, and that a telescope in La Palma saw that it was emitting 100 GeV gamma rays. Now that's very rare. So this was a really special object. I'm not going to explain what this telescope is. It's called MAGIC, but I was there a few months ago. This is on a mountain in La Palma. It's a beautiful place, actually. Now, was anyone else looking? Well, that's what we found out. So it was detected almost immediately by Swift in X-rays. I told you about Fermi. And so at some point, 22 telescopes were looking at this object. And at the moment, there are still telescopes looking at this object. Many of these are optical telescopes. And what they were trying to do is, this was actually a known galaxy. They were trying to figure out how far it was. But the galaxy, they couldn't see it because the light at high energy was so strong they couldn't look through it and see the galaxy. It's only later that a telescope found that it was 4 billion years away. Now that's another surprising thing, as I will tell you in a minute. What is it? It's a galaxy like ours, basically, but instead of we have a galaxy in our center of our galaxy. There is a 2-3 million solar mass black hole, but it's not active anymore. It barely eats some stars nearby. Where in an active galaxy, this black hole is eating up its own galaxy. And it's rotating, and along the rotation axis, it produces a jet that accelerates the cosmic rays. It's like a particle beam. And that particle beam we see in neutrinos, and the Fermi sees in gamma rays. And so this is the first known source of cosmic rays after 106 years. And so it's a supermassive rotating black hole. That's the answer for one source. Here is the paper measuring the distance. 4 billion light years is far away. There are in our galaxy sources like this that are 10 times closer. Should emit 100 times more photons, but they don't. This one does. So why is the first source we see, and the one that's the brightest in the sky, 10 times further away than the nearby ones? Never mind our own galaxy. So there's something very special about these sources. But in the meantime, we have collected so much data with so many telescopes, we are going to figure this out eventually. But what's the chance that this is actually a total accident? The chance is about 1 in 1,000. And 1 in 1,000 happens. You wouldn't be sure about this. But we can do something else. We have collected data now for 9.5 years, many of it while the detector was being constructed, but it doesn't matter. We have 9.5 years of data. We can go and look back at this data. And so now that we know where to look, in what direction, we look back, and this is what we saw. You see, this is 2008, this is 2017. And you see this? That's not what I've been talking about. What I've been talking about is this. You barely see it, you see? There's this one neutrino, there's this little peak. In 2014, we see neutrinos in 110 days. No theorist had ever predicted this. In fact, we're still, at the moment, every theorist in this field has been thinking about this, and we still haven't even been able to produce a model that gives this. And that's typical. It is just a spectacular object. And you see, this is the sky map. It's the 15, and we can measure the energy spectrum. Everything fits together. And the chance of this being an accident is 1 in 100,000. So probably the 1 in 1,000 is real too, right? Given that this is real. So conclusion, we identify the source of high energy cosmic rays. It's an active galaxy. That was its name. It's called Texas. 0506 is where it's in the sky, and it was originally discovered by a small telescope at the University of Texas. And of course, we now have lots of data on this thing. So the conclusion is we publish in Science, and I always sleep well about this, no problems. And after 106 years of his discovery, we finally have a source. So I already mentioned this is an enormous breakthrough for NSF. And so we have now not, we always had cosmic rays, even though they were telling us something about the universe that was incredible, but that we couldn't understand because we couldn't look into that universe. Now, in 1 month, we have 2 new ways of looking at the universe, gravitational waves and neutrinos. So I think I said all that. Capitalizing on a discovery, that means you go back to the National Science Foundation, ask for more money, build a 10 times bigger detector, which we just started the process for. In fact, we even got the first money. Astronomy guaranteed, we will see. And we want more neutrinos, more telescopes, so we get a 10 times bigger detector. They are building a similar detector in the Mediterranean, and they just started the construction, and they are building a detector in Lake Baikal that will be big enough to do what I described to you today. And now, not to get in trouble with my collaborators, I have to show this map, this slide. I have told you about, shall I count, 1/6 of what IceCube is doing. All the rest, it does neutrino physics. Nobody has seen neutrinos of this energy. So the neutrinos they produce at Fermilab have 10,000 times lower energy. We are studying the Earth with neutrinos, totally different talk. We are testing fundamental properties of the universe. We are looking at dark matter. We haven't found it, neither has anyone else. We're doing all kind of exotic physics, but on each of these boxes, we have actually published papers. So this is not propaganda. And so this is a wonderful instrument and would have been worth building even if we hadn't done anything about what I told you today. Thank you very much. I didn't do this by myself. And so I want to show you a picture of the collaboration that was taken at Union South across the street a year ago. Questions?
Is there any understanding of the process that can produce neutrinos with that energy, which is, as you indicated, is orders of magnitude greater than what goes on at Fermilab? Yeah. How do they get produced?
Here is the 15-second version. This black hole is accreting matter at incredible rates. And it chokes occasionally. And when it chokes, it throws out this matter along its rotation axis where, magnetic field is wound up. And so in these blobs of matter thrown out, the black hole, you set up shock waves. These shock waves accelerate protons. This whole system is inundated in light, in photons. So the protons interact with the photons, make pions, make neutrinos. It's all perfectly possible. However, we haven't been able to make a detailed blueprint of this object. It's still challenging the theorist, and but that's the concept. Very basic physics.
Sorry.
Oh,
I'm just curious, what was the environmental impact study for this like? I mean,
like this.
unprecedented type of thing. I mean,
Yeah, it's you can have. Okay, the Antarctic Treaty doesn't allow any activity but science in Antarctica. So there is a committee set up by the Antarctic Treaty that has to approve everything that's going on. And so, we wrote, this is done the government way. There is a company in Washington, and I worked with them in writing the environmental impact statement. And it's published, and then there is a 60-day time for commentary and review. After they approve it, there's 60 days, anyone can complain. I mean, this is what goes into the ice. I mean, the impact is minimal, right? But yeah, you worry about this.
Hi, Francis.
Yeah. Oh,
So
hi, Amy.
What
I haven't
changed?
seen you for a long time.
Great talk. Thank you very
Yeah,
much. I
thank
enjoyed
you.
it. I have some students from Astronomy 103 here. So we've been studying neutrinos in class. I wanted to ask what changed between 2015 and 2018, the fact that you detected the 2000 in your data analysis, because you detected the 2018 event, not the 2015 one originally.
Yeah. Actually, we think that the 2015 event is the real deal. That's what, by the way, if 5% of active galaxies are special like this source, we can explain our diffuse flux. So this could be the final answer. Now, so why didn't we see it? We actually did see it. It's in a thesis of a student at the University of Geneva. The problem is that if our resolution by now is 0.2 to 0.4 degrees. So if you look at the whole sky, that's a lot of trials. If there's no difference between any direction. And so this object was slowly moving its way up to become 5 sigma, but it had not made it. And so, in a sense, all multi-messenger astronomy did was take our trial factor away. And but eventually we would have discovered this thing by ourselves. But this is a much better way of doing it. Also, we would have had no clue what it was, right? It's some direction in the sky. So also notice that if Fermi and others hadn't seen this, we would never known that there was something different about this neutrino. This neutrino is like 100 we have. And Fermi sees flaring blazars quite regularly, so they would never have noticed that this was special. So this is really an example of multi-messenger astronomy doing something that would not have happened otherwise. Unlike all the previous examples, neutron star mergers were discovered by LIGO alone, right? And so this was really truly multi-messenger event. Someone has been asking for the microphone.
Do we know that active galaxies, blazars, is that a function of the age of the galaxy or of galaxies at a particular age in the universe?
Well, as I said, there are, even at high energies, some 5,000 of these objects are known. And, we don't know what's special about this one. That's question number one, I think, to figure out. And we either have figured it out with all the data we have on this one, or we have to figure out by seeing another one. But remember that this galaxy only did this once in 10 years. And so this may take a while. We'll solve this somehow. You know, everything we did happened without totally anticipating it. So we'll solve this problem in some way I cannot tell you now. That's how this science works. Yeah, there was someone in front there. It has been yeah.
Hi, Francis, you mentioned the cosmic neutrino flux that we're seeing is about 120 per year, and I think you mentioned that might be there might be 360.
Of one neutrino type.
Okay.
So for the particle physicist, neutrinos oscillate. Mm-hmm. So as the beam comes from far away, by the time it reaches the Earth, you approximately get equal number of the three types of neutrinos, and so 120 is just one of them, is the muon neutrino that I've been talking about.
We're not seeing the tau and electron
No,
neutrinos.
we are.
Oh, we are.
Yeah.
Okay.
We are. Well, I showed you an electron neutrino. There was no track in the first event I showed you.
All right.
That was an electron or a tau. Now we actually have our first event where we can tell that it's a tau. That's hard, but we've done it.
All right, thank you.
Hi, so you mentioned that you were looking at scaling up the size of the detector in the next few years by a large amount. What are you trying to get out of that? Are you trying to find just better data, or are you trying to find different events?
Both. We are trying to find more events and better events. You know, when these tracks get longer, you can point them better, and that, in fact, pointing is really what we are after, to have better than 0.1 degree resolution. Now, only very rare events we can get to 0.2, 0.3 degrees. We want to get to better than 0.1. And so, but you make it bigger, you get more events.
But you find events of significantly different energy with a bigger detector?
We'll find out.
Yeah.
Yeah, yes, we can get, yes, you get to higher energy as well, yeah. I didn't go into details what the spectrum looks like, but the next question to, you know, does this spectrum extend to higher energies or not?
Hi, I'm a first semester astronomy student, so you gotta bear with me on the question. But when you showed the map of the neutrinos, both in the entire galaxy and the high energy ones, there was a noticeable curve.
Yeah.
And I was just wondering if you could elaborate on what that was.
I said I wouldn't explain that, but I do it quickly.
Sorry.
When the energy of the neutrino goes up, the probability that it interacts goes up as well. So the highest energy neutrinos don't make it through the Earth anymore. And you see slightly more along the horizon than the ones that have to come straight through the Earth. They are more likely to not make it. And that's the structure you saw. The structure you saw is the horizon. And from there we can collect high energy neutrinos, which, if they came from that direction, wouldn't make it through the Earth.
All right, I think we'll bring this to a close. Please join me in thanking Dr. Halsey.
Thank you.
And also, please join us for a brief reception outside, too. Look forward to it. Thank you so very much.
Thank you.